How's everybody doing? So listen, I know that there may be some ML beginners here, which is great. And so they told me to fit like explaining this thing in like 22 minutes. And so if I'm going too fast, if we need a safe word, let's just decide one right now. Do you know what I'm saying? Just so like just let's watermelon. So if like all of a sudden I'm going super fast and you're like, I missed something, we'll use our safe word. Should we practice now? Very good. But no shame. But here's the thing, like I feel like it's the presenter's job to get things across, and if you don't understand, like when I'm sitting in the audience, I don't understand, I feel like I'm the dumb one. In reality, if we can't explain it well to you, it's kind of my job to do that, right? Because it feels like when we talk about this kind of thing, they're like, and then, like, it's basically just a convolutional neural network, and then now we're deciding, like, everything else, right? I feel like that's what happens sometimes, and I feel like we need to have, like, a space to say watermelon. Okay? So that's what we're going to do today. I'm going to explain how convolutional neural networks work, and then my colleague Siyu is going to come up and show you, like, even bigger ones and actual really cool use cases where there might be animal pictures. Oh. That one took me off guard. Thank you for preparing me, Glenn. I'm excited for this. Thank you. All right, so I'm going to talk about how computer vision works, right? We always have to start with this, which is indeed a toy data set or the hello world of all things. So those of you that are data scientists, maybe you'll find a different way to explain this, or maybe just bear with me. For those that are learning, again, safe word. This is what it looks like inside of the computer. When we're looking at it, if you squint into the matrix, you'll see that this is the number S, which is between 6 and 7, right? If I remember right. It's the number 5, right? If you squint and look at this, this is what the computer gets, and this is what it has to decide. And we want something like this, right? This is what programmers want. We want to give it those numbers, and then we want an integer to come out between 0 and 9. And machine learning is an interesting field because basically its job is to find functions such that when you give it something, it gives you the right answer, except that we don't program it. We say, here's some data, and then it comes up with an answer. But the question is, what do these things actually look like? For those that are new, like I had a hard time with this until my professor was like, look, here it is. And I'm like, oh, this is wonderful. Watermelon. That's what I told him, right? So let's do a simpler problem so we can do it in our heads, because I feel there's some good intuition here, because this looks like a part of a picture. And what I'm going to do is we're going to make a machine learning problem that you should never make. We are going to decide whether this picture is darker at the top or darker at the bottom, okay? I'm going to use my fancy clicker here to say this here thing represents this one, and the 1 says it's darker at the top, and these are the values for each of the pixels, okay? Super, super easy. Now, as a programmer, how would you solve this? Our programmer lizard brains, if we engage them immediately, will attempt to solve these right now. How would you solve this problem as a programmer? Average the top, average the bottom, whichever one's great. Here's a little math trick. It turns out that if you divide by 3 both times, it's not useful. So you can just add the top and add the bottom and compare, right? Because dividing by 3 both times really doesn't make sense. Okay, so you were able to solve this with your programmer lizard brains. We all have them. Like we literally in our house upset our loved ones by programmer lizard brains, our tasks, right? Someone's laughing over there because she did it like this morning, right? Me too. Okay, so but I'm going to force you to do something a little bit different, okay? Now that you know you would add them and compare them, I'm going to force you into a specific structure that many of you will recognize but pretend you've never seen. So if there's audible gasps, that would help my presentation. Yeah. So now I'm going to force you to take the numbers of the pixel values between 0 and 255, and I'm going to force you to multiply them by some numbers that you can choose and still get the same answer. How would you do that? What numbers would you choose? So remember, before we thought if we added the first 3 and added the second and compared them, that would be helpful. What would you do in this case? What W's would you choose such that when you multiply them all together and add them up, you get them? I used to teach high school, so awkward silence is mostly awkward for you. what numbers would you choose? What, one's here? Okay, so one's here because that's like forcing an add. What numbers would you put here? 0, right? Because we don't care. What numbers would you put here? -1, right? Super easy, because basically what you're doing is you're adding these all up, but making these negative, and then when you add them, they like fight each other, and whoever's stronger wins. And so if the answer comes out negative, then it's darker at the bottom. The answer comes out positive, it's darker at the top, right? We're good so far, yeah? Any questions? This was a trick question because you all should have said, well, what does that be? See, I'm testing you early to make sure you will say watermelon. What's the B? Well, it turns out that if you want your algorithm to guess that the top is not as dark as the bottom, but just like within 10%, we still want to guess top, then you add a positive number, right? And then it biases it towards the top. If you want to bias it towards the bottom, you add a negative number, right? And then it forces it to guess bottom a little bit more. In machine learning, this has a very technical term. It's called the bias, right? It's true. Okay, so let's test it. Here's a picture, right? We put the numbers in there that you decided, and the answer comes out 236. We guess top. Let's do the negative one. The numbers come out negative. There you go. Super easy, right? Well, that's machine learning. That thing we just invented is called a model, and that thing we did is prediction. I know, and then whenever I do this to people that are not machine learning, they're like, no. Yes, this is a basic perceptron, right? If you put a sigmoid around it, it turns into something like logistic regression. What? I know, I feel bad because then all the data scientists are like, shh, my boss is here. Okay, Seth, you're so smart. What if we want to do top, middle, and bottom? So smart. Well, we just have 3 of them, right? And then it looks like this. Right? And again, I like linear algebra, but I didn't when I went to undergrad because I thought it was the dumbest math ever. And then I went to grad school and did this stuff, and I was like, oh, wow, this is really useful. This, to me, is the Cookie Monster operation when you multiply a vector times a matrix, because I'm 5 years old, basically. You take this vector, you turn it on its side, and you go num, num, num. Right? Which is the thing we did before, but 3 times, and then you get an answer out, right? So these are matrices and vectors, and it's just easier notation. So you turn it aside, num, num, num. Okay, it's going to start to get real dodgy here in a second if you've never seen this stuff before. So bear with me. By the way, this again is another model, but we actually wanted to do the numbers thing. So what do? Well, we just make it bigger, right? And so now this turns into something like this. Does this actually work? For those of you that are data scientists, you can actually get 93% accuracy with a linear model using an atom optimizer. Did you know that? It's crazy, right? And I didn't know this until I tried it. I was like, oh, I got 93% accuracy just doing this dumb Cookie Monster operation. Now, the question you may have is, it was real easy for me to pick the W's and B's myself when the problem was small. But if it's big, how do we get all these W's and B's? Because basically all deep learning is a bag of W's and B in a very fancy network. That's all it is. How do we find them? So let me give you some motivation around how to do this. We want to find a way such that when we find these W's and B's and we do the multiplication, the answer is right. So we want to minimize the amount of mistakes. So now I am going to write some maths. I say maths because everywhere else they have more than one, except here. This is really weird. This function measures how bad we are at doing it. Remember, this is the thing that guesses the right answer, and this is the right answer. Okay? So, let's pretend for a second that our machine learning algorithm predicts a 7, and the right answer is 7. What does this turn out to be? 0, right? But again, these are vectors, so just bear with me here, so think of it that way. Let's just say you guess the wrong answer. What will it become? Not 0. And so what we want to do is we want to find and so when we get not 0 and we square it, it's amplifying the error. So this function tells us how bad we are at it, and then it penalizes us for badness by adding a square. Okay? So this is a really interesting function, right? It's, for those that know, it's mean squared error. But when you look at it, it looks like this thing. This is the h of x that we had before. I forgot to tell you that. It basically looks like something like this. Let's pretend for a second that if you go back, you see there's this huge thing, but there's a square. Let's just make this thing x squared. So a question to you, anyone play Super Mario Brothers in the 80s? Everyone did. If you haven't yet played it, you should really look into it. If you take nothing away from this talk. So let's pretend, for example, that we are living in Super Mario Land, and we can go in two directions because it's Mario Brothers 3. Noah's 3 was the one you could go backwards? Yes. So if you're living right here and you're blind Mario, how do you know where to go to get to where the error is 0, right? Because this function, let's pretend it represents the error, and error is positive here. We want it to be negative. So what would you do if you're standing here? You put your foot down, and you're like, oh, X, Y, down there. And then you put your foot back, and you're like, oh, it's up. And so you measure a little bit of the Y, and you measure a little bit of the X, and you divide it. So let's call it dy by dx. And then, because Mario is really cool, he can take like infinitely tiny steps in both directions. He has really tiny toes. I mean, they're like seriously fractions of pixels. You divide this, and this tells you the slope at this point. And if you know the slope, you know where to walk. Okay? Pretty easy, right? This slope tells us the direction we should walk in. So I'll tell you what the derivative of x squared is. It's 2x. Here's my other thing. It's like, for derivatives of these things, I just think of like these numbers graduating towards the front, and then they miss them so much that they take away one. I don't know why I think this. It's the dumbest thing. I don't know why. So see how 2 graduated, and we took away 1, and just like he disappeared. He's so sad. So let's do a little exercise here. Let's say we're at x equals 3. What's the value of x squared at x equals 3? Rhymes with fine, starts with n. Oh, shoot. You didn't say there'd be numbers, Seth. All right, so 9, right? What's the derivative at x equals 3? Well, we put the 3 in here, and 2 times 3 is 6. Do we want to walk in this direction, the negative direction, or the positive direction? Negative, so we subtract the derivative. So 2 minus 3 is negative 3. Thank you. Let's do this again. What's negative 3 squared? 9. What's 2 times a minus 3? Negative 6. If we're at minus 3 and we subtract a negative 6, that puts us back at, we have a problem. Mario is jumping too far. So what we have to do is we have to scale the step that we take. So we take a fraction of 6 and then do it. This is called the learning rate, and this is called gradient descent, basically. It's crazy, right? This is every time I explain this, we're like, oh, I knew this already. Yeah, you did. It's basically Mario Brothers, right? We take our W's that we have, and we subtract off a scaled step of the derivative in the right direction, and we loop until either it gets to 0 or it doesn't change. Or if it goes up, you stop because he's walking up the wrong side of the hill. And this is what the function looks like. I'm sorry I missed a 2 here. Those of you that are judging me silently in the back, I forgot the 2. And this is the derivative for finding b. Right? Okay, so pretty easy, right? Now that we've done that, this thing, if you have a bunch of them, like let's just say you have this thing and then you have another one here and then another one here, you can start to put them together and you get structures that look like this. So this is a neural network, right? If I just stack them all together? No, right? Because you can prove mathematically that a linear combination of any linear combination is still a linear combination, so you put functions in between. They're called activation functions, right? ReLU, like they told me early on that these functions, Seth, need to be differentiable. They're liars. The ReLU is not differentiable, but still. Right? And so you put a function in between, and then you can get even more complicated structures like this, right? Where you multiply this vector coming in by this matrix. You do a function, ReLU, which is an activation function, which is like a squashing function. And then you do it again, you get smaller, and then out comes the answer. And you just pick the biggest one. And then that's the digit. All right, so it turns out that with pictures, though, you know, because when I take the number and I take all the pixels and I line them all up, I'm losing like pixels that are next to each other vertically. So how do I fix that? So let me show you a simple trick here. It's called filters or convolution. So here is this thing right here. So I'm going to take this square right here, and I'm going to do the same thing I did, you know, where I multiply each space by the corresponding number, so the 1 by the 2, the 4 by the 1, and then I'm going to put it here. I'm going to do that. I'm not going to tell you why, but just go with me on faith here. Okay, so the problem with that is it makes the image smaller, and we don't want to do that. So we can add some pads around it with zeros and then do it again, right? So we can do this here, and then it goes here, and you can see if we go over one by the segments, it's like, again, 80s childhood, it's like Knight Rider. That's the sound I imagine happening when convolutions are happening. I should probably make sounds for that. Okay, so that's good. So that's padding. And now what we want to do, if we want to make the image smaller, we can do this thing called pooling. And this is pretty cool too, because what we can do is we can take, for example, this thing right here, take the biggest number and put it there, do this thing again over here and put it over there. Now you're probably thinking, well, what the heck does this even do? That's a good question. I actually wrote some code to show you what it does. So this is, someone said, is it NumPy or NumPy? Am I like a troglodyte if I say NumPy? Okay, I will say NumPy then. So I made something that opens a picture and resizes it to 500 by 500. And this is, again, the filter. It's a convolution. It's basically the for loops that do all the thing. But if you think about it, it's like a square dot product. Like the thing we did before with the little thing, same thing, except it goes over and I'm doing that again. And then I wrote a little function that does some pooling here. Now the cool thing about this is I wanted to run it over some pictures. So again, we picked our magic ones and minus ones, right? It's the same thing we picked because I wanted to see what it would do. And so I'm going to load up a picture that's really important to me. The wedding. And I am going to run a convolution over that convolution. Look what it does. It like highlighted the edges. Did you see that? Just by doing that operation and showing it. You want to see what pooling does? It accentuates them. Let me do another important picture to me, obviously, of the, let's do one of the kids here because kids are important. So there's the kids. And we do it again, and you can see that it's basically doing the same thing. And then finally, let me do one that's actually like one that's actually not as funny, but like will show you some pretty powerful things. Like here's a fence, and it was able to find like where the slats of the fence were just by multiplying by that over again. Now here's the thing, because of that multiplication that we did is similar to the dot product we did before, you can actually put it inside of neural networks. Like this, and it's basically like a special kind of dot product. So as you're doing this gradient descent to find these W's and B's that live in convolutions, it is actually figuring out a way to make this picture simpler by making multiple pictures, making them small, and then learning them out off of that. That's nuts, right? So when you're looking at these kinds of things, just think about it. It's just W's and B's, and it's something that it's basically coming up with a big picture and then filtering all the way down. Now, Siyu is going to tell you how we actually use this for some pretty cool applications.
All right. All right. So Seth just told you, like, if you had multiple of these filters. So the filters that you just saw, which are 1, 1, 1, 0, 0, 0, negative 1, negative 1, negative 1, that's actually an edge filter if you know, if you've done graphic stuff before. So if you let the neural network have a pick of its choice of filters, like numerous of them, hopefully it will learn different and useful filters to pick out different aspects of different visual cues. So these are pictures that would result in the most activation for different filters in the first layers of a neural network. So you can see that some filters learn to detect edges, like we were just looking at, and then others learn to detect patterns, or like edges at different orientations and color blobs in different combinations. And so in later, deeper layers of the neural network, it actually learns higher level constructs, like this an eye, or a head, or a person, or a house. And then later layers would aggregate this information and give you, say, like a classification if you were trying to do image classification, as with the MINS data set. So if you had, if you stack all of them together, which is like the upper, that upper image there, I think has like something like 54 layers or something. If you use filters at different levels and do other pooling and other operations, and you stack them in a sensible way, then you can accomplish fairly complex tasks, not just image classification, but for example, object detection, which is the application I'm going to talk about today, which actually, given a picture, it will localize, it will tell you where different objects are and what those objects are. And so, so if you look at this diagram, which is the which indicates the object detection network, what it does is that it uses layers from a convolutional neural network from that other side, which is just a longer version of what Seth showed you, and then it goes into two arms. One arm would be proposing different regions on the picture. It will say around which point on the picture and how far is the offset. So it's actually a regression task, and it tells you where these objects should be. And then there's another arm that gives you the classification of each of these proposed regions, and that's object detection, basically. And here are the outputs of a object detector trained on images of common objects. So you see that they put bounding boxes around each object it sees, and a confidence for that object being the particular class shown there. So how can this be useful? So I actually work at a different part of Microsoft, and I work for a program called AI for Earth, which we basically try to help organizations to accelerate solving environmental problems using aspects of machine learning. And one canonical problems in the biodiversity wildlife conservation space is processing camera trap images. So at the top is an image of a camera trap, which is basically a motion or heat-triggered camera that just takes a couple of frames as the animal walks by. And then you result in both daytime pictures and nighttime pictures. And one of the problems, so when ecologists want to study, say, like animal population or monitor their behavior or understand if a particular conservation effort has been useful, has been effective, then they go out and deploy these camera traps and take pictures. And often, like each one of those studies that lasts for a few months, when they get all the SSD cards from all the cameras, they have millions of images, and they literally spend the next year looking over them and process them. And so it just strains their resources, and also the insight that you get from these studies are often just not timely enough. And so we've developed a object detector, and we trained them on about 100K images where we got the bounding boxes around the animals labeled, because to train an object detector, you need not just classification, but you need the actual bounding boxes to be able to train that. And we are able to train one that's generalizable to different ecosystems, and it's really effective. By doing this detection, it's able to tell whether the image actually has an animal or not. And so, because a large, up to 95% of the images are actually false triggers, because you have, leaves blowing around, and things causing the camera to trigger. And that really saves the researchers a lot of times. They can focus on images that actually have animals. And as a next step, we want to train species classification classifiers for the same images so that we can even go a step further as to count the number of different species. It's just that we want to train them for the specific species distribution in each regions. So that would need to be more customized. So how do you get involved? Well, you should visit us at our website to learn more about the AI for Earth program. We have a Azure Compute a grant program that will be really good for something like the Ocker project that we heard about yesterday. If you're working on a conservation problem and want to use aspects of machine learning, you should visit lila.science, where we release some of our publicly, where we host our publicly available data sets of camera trap images, and also some images of aerial survey of African savanna. And all of our code is open source at github.com/Microsoft/camera-traps. So go check out what we do and see if you'd like to contribute in any way. And then also keep an eye out for a detection API and a demo build around that. That's going to be, I'm going to release that soon. And then participate in the Kaggle competition that we sponsored called iWildCam 2019, which is basically working on camera trap images. So this is a cool video. This is just a video of applying our detector to in images, actual images that we get from our partners, and kind of run them frame by frame, stitching them together. I can watch this for hours. So I'm just gonna leave that on for a little bit. Anyone have questions?
We should have spent more time. Like, I should have gone out in the woods and had myself in there to see if it would have found me. That would have been a really good test. All right, so hopefully this was helpful. You got a sense for like how deep learning works, in particular for computer vision, which is really nice. Some of these ideas obviously transfer over to NLP and to speech, which is pretty cool. But I think overall the intuition of what's happening is super important. I don't like the current trend in AI of us making it into magic. It's not alchemy. It's computer science. And so thank you so much for your time. Hopefully we'll see you in a little bit.